Okay, let's get started. So I don't know if you remember me. My name's Joe. I'm going to give you the third installment of the lectures on deep learning. Today's lecture is going to be about deep generative models. There's been a lot of really incredible progress in the last few years. So it's a very exciting area. Yisong told me that you're not going to be tested on this. There's going to be no homework on it. This is just a for fun lecture. So I hope you enjoy it. So generative models. Let's think about what we've been dealing with. So we have usually some matrix of data that we're given, and this is going to consist of a number of entries, the rows of which here are representing different data examples. So you might have examples down the rows here, and then you're going to have a certain number of features for each data example. So this is just the length of the vector for each data example, number of features by number of data examples. And we can take this matrix and we can actually plot it out in this high-dimensional space, and we think about each axis here as defining a particular feature. And in this space, each data example is going to be a point. So each data example has values for each feature. You can plot those in this space. And we can proceed to collect data and figure out what is this empirical data distribution that we have. And it might take this form, for instance. So we have this ring here, and there's some very specific structure that's encoded in this distribution. And what we'd like to do is actually be able to estimate the density in this space. So we'd like to be able to fit a model in the data space that tells us whether or not we should expect a data point to be here. And that is what a generative model is. It's just a model that estimates the density in the data distribution. And one of the cool things you can do with a generative model is that once you have this density estimated, well, you can then sample from this density to retrieve new generated examples. So I might sample points in this space, and these are new data examples essentially, brand new data examples. So just to kind of clarify the difference between what generative models are versus what you've perhaps seen before, if you have a discriminative model, that's trying to discriminate between classes of points, for instance, or it could be a regression problem. And so in this case, you're going to try to draw a boundary and separate out these two parts of the data distribution. But you notice that we're spending a lot of effort modeling here out in this region where there's no data. And yet we're still saying very confidently, oh, that's a red class. And likewise down here, we're spending part of our models to say, okay, this region down here, even though there's no data, we haven't seen any data there, we're still going to call that blue. On the other hand, a generative model is going to try to fit some density to these points. So you notice that we assign here a darker colored red where we've seen a lot of points, and as we emanate out from here, we get lighter and lighter colored, kind of symbolizing that we're somehow less confident about there being data there. And you notice that we can still encode the notion of class. So we can still say, okay, the red points are in this region, the blue points are in this region, and so you can still come away from this with a class estimate, but we're only modeling the data where it is. So just to make it absolutely clear, you can train both of these models with supervised learning, which you've probably gotten quite used to by now. And generative models actually are a little bit easier to train with these unsupervised methods because at the end of the day, it's really about just modeling where the data is. You don't have to have some label that tells you what the data is. But you typically need more modeling assumptions in a generative model. You need to decide how am I going to model the data distribution, not just putting down boundaries. And it's a little more straightforward to quantify uncertainty with these generative models because if you haven't seen data in this region, well, then you're more uncertain. And why might we want to do this? Why might we want to actually model the data distribution? One reason would be that we can actually extract structure from the data distribution automatically. So if we have these sets of points, we might be able to fit a generative model to these two clusters that just says, hey, there's a cluster in this region, and there's another cluster in this region. And the nice thing is that this effectively reduces the dimensionality of the data. So in this 2D example, it doesn't really help you that much. But you can imagine now if you're in a high dimensional space and you're modeling these clusters, if I give you a label for each one of these clusters, it's fairly straightforward to then extend that to the entire cluster and say, okay, all these points probably generalize to this class, and all these other points generalize to this other class. So you can use generative modeling to learn representations that are good for later tasks. Like if you're trying to do classification, it's a great representation learning tool. And just very generally, any model that outputs in the data space is a generative model. So anytime you think about predicting what's going to happen next or trying to reconstruct what you're seeing, that's a generative model. And it's at least very clear in the neuroscience community that there's a lot of top-down signals coming from higher regions of the brain toward sensory inputs. And obviously, humans are able to predict what's going to happen next. We can imagine things that haven't happened. So it's very clear that at least some part of the brain is doing generative modeling in some way. I'm not saying that anything here is remotely like what the brain is doing, but clearly it's a very useful strategy. If all you have is incoming data, then it's a good thing to try to model the structure in that data first so that you can use that structure later on if you're trying to figure out whether something was good or bad, or if you need to learn the name of something. And today, we're not just going to be talking about any generative model, we're going to be talking about deep generative models. So we talked previously about these deep networks, and a deep generative model is just a generative model that uses some component of depth in its modeling. So we're going to be using deep neural networks here, although we're not going to get really into the details of the deep networks themselves. And there's roughly 3 families, I would say, of these deep generative models. The first that we'll talk about are these so-called autoregressive models, where you use previous estimates to estimate later estimates of data dimensions. And then the next component is going to be these latent variable models, which really are using explicit probability distributions to model the data using latent variables. And then we're going to be talking about these implicit models that do not have an explicit probability representation, but nevertheless can learn this data structure, although implicitly. So, and stop me if there's any questions. So we're going to go through each of these families today. That's going to be the lecture. So what are autoregressive models? So say we have some data example here, and I'm representing with these circles each dimension of the data example. So each circle here represents a feature. So we might have x1, x2, x3, all the way up to xm. So we have m features. And we can model this data example using a joint probability distribution over each of these features. So that's represented here, where we've taken bold x here to represent the vector of the data example, and then that's just spread out over this joint probability distribution. So if we take this data example, we can use the chain rule of probability to actually split up this joint distribution into a product of conditional distributions. So what is the definition of conditional probability? That just says that the probability of some variable A given some variable B is their joint probability, represented here with a comma, divided by this marginal distribution, which is probability of B. So what is the joint probability of seeing A and B divided by probability of just seeing B? And so we can split that out if we rewrite it into this joint probability is the conditional times this marginal probability. So this hopefully is all reviewed. And we can apply this definition recursively to any joint distribution. And so at the first stage, we might say, okay, this joint probability distribution over x1 to xm, well, we can write that as x1 given everything else, and then take the probability of everything else. So we're just replacing b here with x2 through xm. And if we apply this recursively to our joint probability distribution, well, then we can get this chain kind of structure where we take the probability of x1 given everything, probability of x2 given what's left, until at the very end we just have the probability of xm at the end here. So we've applied this rule over and over. And note that the conditioning order here is absolutely arbitrary. You can condition it in any way. And with this, we can rewrite this joint probability distribution as a product of conditionals. Now, what we're going to try to do is actually model these conditional probabilities. And in a sense, what we're going to do is auto-regress to these missing values. So if I have this, this example here that is completely empty currently, well, I can say, okay, what is the probability over this first entry? I'll assign it. And then I can use a model to say, okay, given that I have this first entry for x1, what do I think x2 is going to be? What is the distribution over x2? This conditional probability here. And I can just repeat this over and over again. I can use different models, or I can use the same model, and I can repeatedly calculate these conditional probability distributions, which give me, again, this joint distribution over the entire example. So I can keep going and auto-regressively generate this data example. Yeah?
In practice, would you limit the scope of like how much you're auto-regressing? So like, would you like an AR1 versus AR12 model, that kind of thing?
Yeah, so you think about like, instead of conditioning on everything, you could say, okay, well, what if I just conditioned on some window? And you can do that, yeah. So what we're going to try to do is actually fit this conditional probability model to the true data distribution. And we're going to do that through maximum likelihood. You've probably heard about maximum likelihood estimation. It's kind of what everyone uses in machine learning, but let's just quickly review it. So we have this probability density or probability distribution here, px, and that's just, again, this product of conditional probability distributions. These are autoregressive conditionals. And we're going to try to optimize the parameters of these conditional probability distributions such that we have a very large probability of actually generating the true data. And we can take the logarithm of this likelihood because it's a monotonically increasing function, and that allows us to actually split out this product here into a sum. So it's just a convenience for actually doing the modeling, but it still remains that the optimum of this probability of this likelihood is going to be the optimum value of theta for this log probability here. So we're going to try to learn the parameters that maximize the log likelihood. So how would we actually set up one of these models? I think the most obvious one is a recurrent neural network. We talked about those in the second lecture. And you can take this recurrent network, which has this loop in it, remember, and we can unroll it in time. And here you see that we're actually taking in this, this x at the bottom here, and we're outputting some output O, and that's getting fed back into the model. So we're perhaps maintaining some state in our hidden state here, and we're feeding the outputs back into the model at each time step. And you can also think of, well, maybe we don't actually want to feed the output itself, maybe we want to feed kind of the true label that we wanted, and so that's just called teacher forcing. It's a common method of training these models where you actually feed the correct output and not what you generated. But at test time, you would be feeding in exactly what you generated. And if you want to learn more about this, the deep learning textbook has a nice chapter on it. So some examples of this are if you had, for instance, a character level RNN that's just trying to model characters in speech. So you can imagine feeding in an H, and it will say there's some distribution over what character should come next, and it might say, okay, I think an E is the most probable next letter. If you feed in this E, it's going to say, well, I think that an L would be the next most probable one. And you can see how you could construct the word hello just by assigning, well, once you've generated HEL, the next one's probably going to be L and then probably an O. And you can imagine doing a similar thing for images, where now I give you a certain set of pixels up to a certain pixel in the image, and you want to say, okay, what is the distribution over this next pixel? You would imagine it would probably be very similar to those other pixels, but you want to figure out a model that actually can model what is the distribution over this next pixel. And you can do this in different ways. Either you can feed in like the entire context up to that pixel starting from the top corner, but remember this ordering is arbitrary, so we could do it at like a multi-scale type of resolution where we pick out pixels at some very dense or some very coarse mapping, and then gradually refine it to get to a denser and denser mapping as we're generating this image. So there's different ways of setting up how you feed in these inputs. And we could also use convolutional neural networks. So like we were saying before, you could use just a window around whatever value you're trying to generate. And there's a popular model called a pixel CNN that just looks at this local window right here in order to condition the generation of this next pixel. And so you can imagine it looking something like this, where now you've taken all this context, and now for this particular pixel here, you have this distribution over, for instance, 255 values that this intensity of RGB could take. And you have to be careful here because if you stack multiple of these layers, you can end up with these so-called blind spots. And so I would encourage you to look at this paper if that interests you in trying to come up with better autoregressive models of images. And another very popular model, I think we touched on it before, is WaveNet. So WaveNet is this model that was trained to do speech synthesis, so you're actually trying to generate speech. And here we're taking, again, a convolution over space, or over time here, and this convolution is actually what's called a dilated convolution, meaning that it actually looks over these very extended windows here. So how would we actually model the output distributions? We could think of having a categorical variable that we're trying to generate, and in that case we would probably want to output a multinomial distribution, and you can achieve that through using a softmax. But alternatively, we might want to model like a continuous output, and in that case, we could use a Gaussian distribution or a logistic distribution or some other type of parameterized density. So some applications that you're probably very well aware of, if you're typing something in your phone, you're probably going to get a recommendation over what word is going to come next. That's not an autoregressive model. So it's conditioning based on everything you've typed up to this point, what are you most likely to type next? And so here you can say, or here you can see that if I've typed, how do you want to go to the, and the next, like there's a distribution over the next words that will occur, and based on, for instance, what this person has typed, it might be beach, gym, or mall. And then you can also imagine if you have like part of an image, you could generate the rest of that image. And again, it's a probability distribution, so you're going to get different samples depending on how you sample this thing. And so you can imagine here with like this top image of perhaps somebody or something in the water, you can generate different plausible images that could have occurred from that top half of the image. And here you have like a dog that's being generated in different ways. And a very cool one, as we talked about, is WaveNet. So if you'll stick with me for a second, I want to show you, if you haven't already listened to it, what it sounds like.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
So you can compare this with, I don't know if you're familiar with what speech synthesis used to sound like.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser. The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
So you can see that it's much smoother, and there's some details in actually getting it to produce sensible speech. So obviously it maybe can't pick up on exact words, so you need to train it in a certain way to actually tell it what word you want to generate. But you can see that you can actually do some pretty amazing things. I don't speak Mandarin Chinese, but
第一班商业航班在1919年来往于美国和加拿大。
I don't know, does that sound plausible to anybody?
Yeah.
Okay. So one interesting thing is that, as I said, you can train a model where you're not telling it explicitly what to say. So this would be kind of the regular autoregressive format, and in this case you get some kind of gibberish out when you generate.
those lessons. Is lot of work I can't tell him what the name because I'm Jeff favorite. Tell you if they're not bad feel him.
So it's just kind of this gibberish that comes out that sounds vaguely speech-related. And it's really interesting because they actually say that a lot of what they found modeled by this model is the kind of breathing sounds that people make when they're actually speaking. Those are things that you wouldn't really get with one of these parametric models that people were using before. So there's a lot of these very unique parts of human speech that you can actually model here.
Can you put a parametric Mandarin just out of curiosity?
Yeah. I think even I could tell that it's not very good, but I'll let you.
第一班商业航班在1919年来往于美国和加拿大。
I don't think I can tell the difference.
Yeah?
第一班商业航班在1919年来往于美国和加拿大。
Yeah, sounds the same.
All right. Your ear is much better trained than mine, so I'll defer to you. So let's recap autoregressive models real quickly. So in this case, again, we take some input, and remember the ordering is actually arbitrary here, so you have to impose this ordering. And based on that input, you try to calculate this conditional probability distribution. So we're autoregressing to these missing values. So what are the pros of doing this? Well, it's actually really tractable and straightforward to evaluate the log likelihood here. Everything's observed, so we can just calculate these things in closed form. And we can really capture the details. There's a lot of these very minute details and images and speech that these models can pick up because it's really modeling these very local interactions typically. And typically, in terms of quantitative performance of actually being able to model the data distribution, in terms of, at least in log likelihood, these models are typically superior. They do very well. So what are the cons of using a model like this? Well, you typically don't get this kind of high-level global structure extracted from the model. It's modeling these small local interactions and not modeling at some higher global level typically. You need to impose this conditioning order. So again, this is completely arbitrary, and maybe for things like speech, it's fairly straightforward to just say, okay, the next time step is going to be generated based on just a past window. But if you're dealing with some more complicated data structure, that might not be obvious, and so that's another consideration. And these models are by far the most computationally expensive because you have to do this sequential process of sampling during training and at test time. And there are ways to speed it up, but it's still by far the most computationally intensive. So the next thing we'll talk about are these explicit latent variable models. And why might we want to introduce the latent variables into our model? Well, you can think of like reality, in a sense, as being composed of these latent quantities that you can't directly observe, that through the laws of nature would generate these stimuli. So we don't think that necessarily the image that's on your retina is all that's out there in the world. We typically would say that there's some object out in the world that generated all of those pixels together. So you might want to try to model, instead of just the local interactions, you might want to model the object itself, and then perhaps add in other components that would do some of these local interactions. And then, obviously, our brains are capable of taking this input signal and inferring some of these latent causes. So we might want to use latent variables to actually model some of these phenomena. And probabilistic graphical models give us a really nice framework for actually finding out these relationships between these random variables. So I'm going to quickly go over what's called plate notation. It's just a kind of shorthand for writing down these graphical models. You don't need to know it exactly, but it's typically useful. So you have these circles here which represent variables in your model. And if the circle is shaded in, that means that the variable is observed. So this is like the data examples that you actually have. And if the circle is not shaded in, that means it's unobserved. It's a latent variable, kind of like the class of object that you're looking at if the observed variables are the pixels. And you have two different types of relationships that you can have between variables. In one case, you have these directed relationships. So this directed arrow here defines a conditional probability. And this undirected connection here defines a potential function over these nodes. So it's kind of like an unnormalized probability. And then the reason we call it plate notation is that you have these plates here, which is just this curved kind of rectangle around these variables. And that just signifies that you have perhaps multiple copies of these variables. So here, if we had n data examples, we'd have this capital N and this plate around x, just to signify that we have n of them. So let's kind of go back to autoregressive models for a second and think about how we might represent that in this plate notation. So we have, for instance, 3 variables here, x1, x2, and x3. And we might say, okay, we know that there's these conditional probabilities. Let's say that we have x2 given x1, and then we say that x3 is generated based on x1 and x2. And then we have, again, n examples of this. We put this plate around the variables. And then in all of these conditional probabilities, we have these parameters theta that are helping in this generation process. So again, we have first some distribution over x1, then we generate x2, and then we generate x3. So that's plate notation for these simple, fully observed models that we've seen before. You have a question?
Are the thetas all the same for each of the n?
So they can be. So you can do like this weight sharing in recurrent networks and convolutional networks, but there's really nothing stopping you from having different sets of parameters. If you had like a fully connected network that needed a fixed set of parameters, you could have a fully connected network for each of these conditional probabilities. So let's compare what we would have with a latent variable model. So we had this for our autoregressive model. Now, in a latent variable model, instead of modeling these low-level conditional probabilities, we might instead introduce this latent variable that tries to capture some global structure in the data. And so in this case, we have z here, which is unobserved, but generates a conditional probability for each of these variables here, x1, x2, and x3. And then there's, again, these parameters which are setting perhaps a prior p of z on z, and then also helping it generate these conditional probabilities. So we've introduced this latent variable here to help capture kind of some coherent global structure. And I was going to talk about undirected models like restricted Boltzmann machines, but I don't think we're going to have time for it, so I cut it. But I would encourage you to look. There's a nice example in the deep learning textbook. There's a lot of tutorials out there. Restricted Boltzmann machines were really the tool that allowed people to initially learn representations when deep learning was just picking up recently. So I would encourage you to go look at them. So what we're going to be talking about today is actually directed latent variable models of this form. And let's go through kind of the typical operations you might want to perform with this. So to actually generate from this model, we define the generative model as such. So remember we talked about how you can split up a joint probability distribution into a conditional times this marginal probability here. So we're going to take a probability distribution over x and z and split it up as probability of x given z and then the probability of z. So this is the joint, the conditional likelihood. So this is the likelihood of the data conditioned on the latent variables. And this here is the prior on z. So it's your prior you have on what types of latent variables you would expect to observe or have. So in order to sample from this model, we would first sample z from p of z, and then use these samples of z to sample x from p of x given z. And this is called ancestral sampling, just based on you sample z and then those are the ancestors that go on to sample x. And so to give you an intuitive example of how this might work, say I had this model of kind of the different probabilities of objects and lighting and backgrounds that you might have in the real world, then I could put that model, put the prior distributions I have over these quantities, put that through some renderer like a graphics engine, and then I might get out natural images. So that's just trying to sample from this model of the world what types of images you might see. Another thing you might want to do in these models is what's called posterior inference. If you're not familiar with it, the idea is just that you would like to, for a given data example, infer what is the distribution over Z. So given that I have this data example, what are the latent variables that would go with this? And this is just the definition of conditional probability again, where you have this joint distribution over X and Z divided by the marginal of X. And here we call this the posterior probability. This is the joint probability, and this is the marginal likelihood. So likelihood is always likelihood of the data, and this is the marginal likelihood because we've integrated out the latent variables. So we can use Bayes' rule here, and this provides conditional distribution, as I said, over the latent variables for a given image, or for a given example, I should say. So as another intuitive example, say I have this observation of a cat, and what posterior inference says is, what is the probability that I'm observing a cat given these pixel observations? Or more generally, what is the distribution over all objects, all backgrounds, all lighting conditions given this observation? And so in order to do that, so cat might be one value of a variable capturing what object I'm looking at. So I might try to calculate what is the probability of cat given this image. And again, you just kind of plug and play Bayes' rule and output a distribution. And the final thing we might want to do with this model is actually evaluate its performance. And in order to do that, we want to, again, evaluate the likelihood. So how well is it fitting the true data distribution? In order to do that, we just integrate out over the joint distribution, we integrate out the latent variables. So again, the marginal likelihood, joint distribution. And we need to do this marginalization step. And what you can think of this as doing is actually, considering all possible underlying states in your model, what kind of a data distribution does that give you? So if I've never seen a particular object, I wouldn't be able to imagine that object necessarily. So if you can think of like if your space of objects that you know is larger, you'll have a better representation of the true data distribution of the world. So another intuitive example, if I have this, again, observation of a cat, how likely am I to generate this example given my model? So what is the probability that I would actually observe this? And then in order to actually calculate this, I would need to say, okay, for all objects and lighting conditions, background, etc., how plausible is this example? So this is integration, this marginalization step. So we actually want to do this maximum likelihood again, same procedure as in autoregressive models. But again, now here we have to marginalize over the latent variables in order to evaluate this likelihood. So before, in autoregressive models, everything was observed, so we can just plug in these conditional probabilities. But here we actually have to take our model here, this p of x and z, marginalize out z in order to get p of x. And this is an integration in high dimensions typically. So it's really actually intractable to perform exactly in most cases. So in order to get around actually doing this integration, one technique, there's a few, one technique is to optimize a lower bound on the marginal likelihood. And so I'll explain how we would get to that. So what we might do, if you follow me for a second, is introduce, instead of the true posterior, we would introduce an approximate posterior. And then we would then take this approximate posterior and try to get it as close to the true posterior as possible. And I'll show you in a second why that's helpful. So you can think of this as like if we had some true posterior that was really difficult to evaluate exactly. Remember that calculating the posterior requires marginalization. Well, if we had this distribution here, maybe we could fit a Gaussian as close as possible, or some other simple distribution, to try to match the true posterior. And instead of actually calculating this KL divergence to match these distributions, you can do a little bit of math and show that you can actually optimize this quantity L, which is the evidenced lower bound, or otherwise known as the elbow. And it's defined as this, which is just the log of the joint minus a log of your approximate posterior, with the expectation taken over your approximate posterior. And this elbow here actually gives us, as the name says, a lower bound on the model evidence, which is the log likelihood. So we can actually use the elbow here to approximately learn the parameters. So that's all variational inference is doing, is it's instead of actually calculating this true posterior and actually marginalizing, you just introduce a simple model class or a simple distribution, try to match it to the true posterior, and then that gives you a way of both doing inference and learning the model parameters, at least approximately. And yeah, it's one of the main techniques used in this area. Yep.
So that maximization is equivalent to minimizing KL divergence, right?
Yeah.
Okay, just for some specific model class.
For any, so this is saying given some set of Qs, some set of approximate posterior distributions, like if it's just Gaussians, or maybe you're trying to fit Laplace distribution or something else, given this set of Qs, the actual approximate posterior that would minimize the divergence between my approximate posterior and my true posterior is going to be the same value that would actually maximize this elbow. And that's just based on some arguments of breaking down this KL divergence into a few terms, and what you get is the elbow and the actual log likelihood. So let's try to interpret what is this elbow. It seems arbitrarily defined. Can we get any intuition as to what it's actually encoding? So if we split out this joint probability distribution, again, just using this chain rule, and then we, again, log of a product just turns into the sum of those logs. And then now the definition of KL divergence is there should probably be a minus sign. Okay. And either way, there's the definition of KL divergence is the expectation over the top distribution in this ratio of one distribution to the other distribution. So we can write out here a reconstruction term and a regularization term. So why are these reconstructions and regularizations? So this is saying, given that I have sampled Z from this approximate posterior, you can think of the approximate posterior as like a latent representation. Given that I've sampled Z from this latent representation, I want to maximize the log probability of whatever example this is corresponding to. So I'm trying to represent the data by actually maximizing this log probability of that data example. And then this KL distribution is just quantifying, okay, you need to actually make sure that the approximate posterior is close enough to your prior. So you have some prior on what Z should be, and Q should not diverge from that too far. So Q needs to both represent the data and stay close to the prior. And there's a lot of connections in this area to compression and information theory. It uses pretty much the exact same terminology. So if those areas are of interest to you, I would definitely recommend looking into this. And you can think of this as like an auto-encoding framework. I think you might have touched on auto-encoders before. And so that's what we're going to talk about, is that you can think of trying to maximize the elbow for each data example here as trying to find the best approximate posterior for each example. And you can solve this with standard gradient techniques. So there's some stochasticity in here perhaps, but you can do this through gradient descent. You can solve this optimization problem of what is the best approximate posterior for this data example that I have. And you can look at this. Here's a 2D space where now you've initialized perhaps some estimate in this 2D space, and you can do gradient descent and jump around here and get to a local maximum. So that's this red star here. which here happens to actually be the global maximum. And you can get pretty close. And there's some step size issues you have to worry about, and there's stochasticity in it, but you can do gradient descent to get to a good estimate. Alternatively, what we could do is actually learn a model that would output these estimates for us. So in this case, we have a kind of autoencoder style of model, which is here called a variational autoencoder, where now you take your data example, you feed it through this inference model, you get out an estimate of what your approximate posterior is, and then you sample from that, put it through your generative model to actually get to your kind of reconstruction. And you can train this entire thing using stochastic backprop, which we talked about in previous lectures. So just some extensions that have built upon this. You can have a hierarchy of latent variables. And the reason you might want to do this is in order to actually capture additional higher level structure if you think that maybe the structure underlying your observations is hierarchical in nature. So here you can see how, given a hierarchical model, you can extract different kind of levels at each model of abstraction here, where here you're modeling, for instance, just like color, like the actual global color of everything. In this case, you might be modeling some intricacies in the structure itself. Here you're modeling kind of the identity of what's going on, and here maybe some other high-level structure. And people have built up these pretty intricate models to do this hierarchical inference. You can also think of having a sequence of latent variables, where now you have latent variables generating latent variables at the next step, kind of in this autoregressive type of fashion. And you can, again, apply ideas from variational inference and variational autoencoders to this problem. And what I've actually worked on is these iterative inference models, where instead of feeding in the data example, you actually feed in this approximate posterior gradient. And so you're actually learning how to do inference sequentially over multiple time steps to improve based on this error signal. Yeah. So what we've talked about up to this point is that introducing these latent variables is really, it's given us some benefits in terms of modeling global structure, but it's really been a nightmare because now we have to resort to all these approximate inference techniques to get around the fact that marginalization is typically intractable. And you can think of this as like, if you had to recognize something by thinking of every possible thing it could be first, it would just, you wouldn't be able to survive. You can't possibly consider all possible hypotheses for every single data example you encounter. So there's another side of latent variable models, which uses the change of variables formula to actually evaluate the log likelihood exactly. So let's get into that. You can actually use this change of variables formula, which we'll go through in a second, to evaluate the log likelihood. So what is the change of variables formula? Consider, for instance, if you just had one variable, or a variable in one dimension. So now you're sampling x here from this, for instance, uniform distribution between 0 and 1. And what if we take this variable x and transform it in some way to get to some variable y using this affine transformation of 2x plus 1? So you can think a uniform distribution, it has to integrate to 1. So what this ends up being is that we kind of stretch out this, this distribution into a uniform distribution between 1 and 3. And actually, to conserve probability mass, you can derive that the probability of y in this transform variable has to be the probability of x times this absolute value of the derivative of this transformation. You can think of this as like, why would it be the absolute value? Well, it has to be the same amount of mass that you're transforming. So if you had a positive area or a negative area, it still has to be a positive kind of mass. So that's why you have the absolute value there. And in higher dimensions, you can generalize this to the following formula, where now you have this determinant of the inverse Jacobian of the transform. And this quantity here, it's a little intimidating, but what that's expressing is how are you transforming the volume in some local space. So in doing this transform from x to y, how are you changing the probability volume here? And this is also sometimes referred to as the law of the unconscious statistician, which I think is the funniest name for a law, where you actually can evaluate expectations and draw samples from this transformed probability distribution if you know the initial probability distribution and this transformation. So you can do this kind of equivalence between the two spaces if you know the transform and if you know the initial space. And this might actually be tractable to evaluate. So here again, now maybe we can evaluate this log probability of this new space if we knew these other quantities. So we need to evaluate this determinant of this inverse Jacobian. And in general, evaluating a determinant is going to be order of n cubed, where n is the number of dimensions here. And so in order to prevent having to actually evaluate this n cubed determinant, we could restrict our set of transforms to these sets in which the inverse Jacobian is either diagonal or triangular. Because in this case, what we end up with is you can take the determinant very easily just by multiplying the diagonal entries together. So it's order of n, which is much more beneficial. So we might want to just stick to these types of transforms. And you can think of this, this entire scheme of a change of variables as just like molding the data in a way that makes it easier to model. So here, what we have is these two half moons here. And what I don't know if you can see the grid, but you transform this space into the space of, for instance, an isotropic Gaussian. And if you look very carefully at these lines, you can see how we've warped the space essentially to bring this complicated data distribution into a simpler data distribution. And likewise, you can do the inverse transform, which is take this Gaussian distribution, and here you have this rectangular grid, and you warp it back into the data distribution, where now you see that you've had to really stretch and shape the space in order to get it back into the data distribution, and yet it's a completely invertible transform. So it's an equivalent kind of ways of representing the data. It might be, or it is easier to model the data in this space where we know how to fit Gaussians to this space than to try to model it in this space where it might just be a lot more complicated. And you can also use this same idea in variational inference in what's called normalizing flows. So the key idea is just that instead of restricting our approximate posterior to some simple distribution, you can actually extend that now to a much wider class of distributions, where now you can think of, you pass your data example through this inference network, and you do a series of these transforms to get to a more complicated, or an easier to model space actually, and then you sample from that to get down back to your generated example. And you can actually visualize how this changes the distribution, where now, say if you had just a Gaussian distribution, well you can stretch and shape that in any number of ways to get to a much more complicated distribution if that's what you need. And so this is actually a really useful technique. And you can chain multiple of these transformations together, as you can see here, where you can imagine if you had this example of this kind of space, you can take some very simple distribution, this Gaussian distribution, and shape it in a bunch of ways, again, all using neural networks, to eventually kind of mold this space into this target data distribution that we're trying to get to. So you're using multiple transforms chained together. And so what do these transforms actually look like? I won't spend too much time, but some early transforms had this kind of form where you just copy half of the data and then transform the other half of the data using this affine transform. In normalizing flows, they particularly use this planar flow, where you take your data, or you take your input, and you, again, do this affine transformation on it, pass it through nonlinearity, then do another transformation on it. Similar thing with this affine coupling layer with this additive coupling layer. Inverse autoregressive flow is a really cool one because it does a very simple kind of whitening operation where now you just subtract off some value and divide by some value. So you can think of this as kind of like a normalization step. And then there's a recent one called masked autoregressive flow, which is just kind of the inverse of inverse autoregressive flow. And so these are all sets of transforms that have these nice properties of either triangular or diagonal inverse Jacobians. So it makes them very easy to actually model. So just to go over some recent work in this area, there's this paper called NICE, which stands for Nonlinear Independent Components Estimation, variational inference with normalizing flows. This is density estimation with real NVP, which NVP stands for non-volume preserving transforms. And then this is inverse autoregressive flow. So these are all papers that have kind of built off of this change of variables formula, and you can see how they're able to model images quite well using this procedure. So it's a really nice trick. If you're not familiar with it, I hope you take a look at it. So just to recap, these explicit latent variables, we introduced these unobserved variables z into the model to try to capture some additional structure beyond these local interactions. And we saw that it created some difficulties in actually calculating probabilities, doing things like inference here. But it also gave us some benefits in terms of being able to model perhaps more expressive things. So what are some pros of this method? Well, you can capture these abstract variables, and in practice, these models are just fantastic for doing semi-supervised learning, where you can just, like I alluded to in the beginning, give a few labeled examples, and based on the representation that you've learned through this generative model, very quickly generalize to other instances that haven't been labeled yet. It's relatively fast to actually sample from these models and train these models as compared with these autoregressive models that we talked about before, because it's just one pass through the model typically. And there's a lot of really nice theoretical foundations from information theory. So there's a lot of work that's been built up that's only just recently started to be ported over to machine learning and deep learning. So there's just a lot of area for improvement. Some of the cons of this method would be that, again, you have to do this intractable likelihood estimation. You have to make some additional assumptions about what priors are we going to have on these latent variables. Like, what kind of variables are we even going to have in the first place? Are they going to be continuous or categorical or binary? What is the structure of that part of the model? So you have to make some additional assumptions here, which may or may not be correct. And it's often the case that these models typically are not able to capture these small details, particularly in things like images, where you get typically very blurry reconstructions or blurry samples out of your model. So there's a lot of areas where these models could improve. Okay, the final area of generative models that we're going to talk about are these so-called implicit latent variable models, or just implicit models. And this is a relatively new idea, and so it's garnered a lot of attention. It's a very exciting area. And the main idea is just that instead of using these explicit probability densities that we've been using up until this point, what if we learned a model that actually implicitly defined this density? And just in a sense, if you had some data distribution here, P of x hat, this is the true data distribution, you might learn a model that could actually draw samples from a distribution that's close to it, but is not explicitly representing this probability. So you might try to represent, for instance, a stochastic procedure that would allow you to sample from this model distribution, and you can devise ways of actually training this distribution to get as close as possible to the true data distribution. So before we get to GANs, because GANs is the main one, this area is actually bigger than just GANs. There's a paper from 2013 called Generative Stochastic Networks, where you're actually defining an autoencoder that learns how to take Monte Carlo steps. So you're actually jumping around in some distribution that you have and transitioning between samples. And so you're learning how to do these transitions. And so the autoencoder here is actually implicitly defining how the distribution is defined. So there's no area in which you're actually saying it's, there's an explicit probability of the data. It's just that you've learned a model that can make jumps in this data space that looks somewhat similar to the true data distribution. But as we'll get into now, generative stochastic networks are not really used in practice. typically what people use are generative adversarial networks, which we'll now discuss. So you can think of one way of estimating the density, or the ratio of the density of these two densities here, would be through what's called a Bayesian two-sample test. And what that means is that I'm going to draw one sample from one distribution, one sample from the other distribution, and I want to see whether I can distinguish whether these samples are from different distributions or not. So if I have this data distribution P of x hat here, and a generated distribution, this is my model distribution P of x tilde, then I can define the ratio of those probabilities as this class conditioned ratio here. And using Bayes' rule, you can write out this likelihood, this conditional likelihood, as then the likelihood of the class posterior probability times the marginal likelihood divided by the marginal of that class. So this is just a straightforward application of Bayes' rule to the top and bottom of this fraction. And then you can, if you assume equal distributions of true data distribution and model data distribution, then you can just simply write the ratio of these densities as a discrimination task of, is this from the data or is this from my generated distribution? So if you can discriminate between these models, that provides a learning signal for improving the density of your model. And this is the main idea behind generative adversarial networks, which are referred to as GANs. So we have this generator component of the network in which we sample some latent variable from some distribution that we have. So Z is sampled from P of Z. This could be a uniform distribution or a Gaussian distribution, some type of distribution, typically a simple one. And you pass that through a generator model. This is always a neural network, but it could be in general anything. And then you sample from this generated distribution x tilde. Likewise, you have your data distribution x hat, which is sampled from your true data distribution P of x hat, and you pass both of these samples to the discriminator, which is denoted as D here. So we want to be able to discriminate with this discriminator the probability that this was from the data or the probability that this was generated by our model. So because it's a binary class estimation, it's just D of x and 1 minus D of x for these probabilities. And you can think of this as a Bernoulli outcome, where now you're modeling the log probability as just the log of D of x hat plus a log of 1 minus D of x tilde. And this gives you a way of actually training both the discriminator and the generator, in which now you're trying to maximize over the discriminator the probability of being able to distinguish between the data distribution and the generated distribution, and the generator is trying to minimize that probability that it's actually going to be kind of recognized or discriminated. So based on this two-sample criteria, it's not actually what people typically use in practice. So you wouldn't actually do this optimization jointly. You would first maximize for the discriminator, then take a step and maximize for the generator, then go back and maximize the discriminator, and do this alternating kind of optimization process. So this down here is typically what people use to train these models. And there's some really nice code examples online. I would encourage you to check those out if you're interested. So just to give some interpretation of what's going on, if you have this data manifold here, where each line here defines kind of the manifold that the data lie on, so each line here is the data, and this space in between is there's no data there. What a explicit kind of maximum likelihood model is trying to do is fit as best as it can this distribution to this manifold. But you can see that it's going to miss out on certain areas just because the fact that you're using this explicit probability distribution limits you in some ways. You have to conform to Gaussian distributions or whatever kind of distribution form you're using. And so typically these models do fairly well at capturing the data distribution, but they can miss out on certain components, and they typically leave a lot of the details kind of under the rug. Whereas one of these implicit models, typically, at least the conventional wisdom is that they are able to capture much better because they're not limited to explicit probability distributions. They're able to capture the data manifold much better. However, they might miss out on regions of the data manifold because they're not explicitly encouraged to model, for instance, the entire data manifold. What you end up with is this thing called mode collapse, where maybe the model is modeling one part of the data manifold very well, but it might not, for instance, get the entire thing. And there are some issues with GANs, one of them being that they can be difficult to optimize. So here I'm showing some examples from a fairly recent paper where they showed that if you change whether or not there's batch normalization in the network, you can end up with like these really not very good looking generated images, whether you're using like a fully connected layer versus a convolutional layer, whether you're using a really, really deep network, you can end up with situations in which these models are just really difficult to optimize. And you can think of this as like you're trying to optimize these two components of the network in an alternating fashion. Like there's not very many guarantees that you're going to find really a good optimal estimate for these networks. Another issue with GANs beyond just the optimization difficulties is that they're generally very difficult to evaluate. So how do you know whether or not your model is performing well? So we don't have an explicit likelihood anymore. So how are we going to quantify the performance? And one method that people have proposed recently is this thing called an inception score. And it's a really fancy term, but it just means that you take one of these inception models that's been trained on ImageNet, and you're going to quantify the class and distribution entropy of what you generate. So you're going to feed in your generated examples through this inception module and see, based on the ImageNet classes, what is the distribution over classes for a particular example, and then what's the distribution over classes for all the generated examples that you've generated. So this is quantified using the KL divergence between this probability of the class for a particular image, and then the probability of over all classes, what would you typically generate. So this P of y given x, for a given image, you want this to be very peaked. So you'd like to be able to generate an image that looks very much like a real class, a real image class. But then this P of y here is the marginal class distribution, and you'd like this to be more uniform because you'd like to be able to generate a large diversity of different samples. So that's one kind of heuristic that people have been using. There's still a lot of ongoing work in trying to actually quantify how well these models are performing. Another really cool extension that gets very theoretical very quickly is this thing called a Wasserstein GAN. And I'll kind of very briefly walk you through the intuition behind it, but if you're interested, you can definitely check out the paper. For a normal regular GAN, you can show empirically or theoretically that it's for an ideal discriminator, so a discriminator that's performing optimally, the generator is actually trying to minimize this Jensen-Shannon divergence between the real distribution and the generated distribution. And that's just defined in terms of KL divergence. It's just a way of quantifying how far these distributions are away from each other. But under certain conditions, this metric is actually discontinuous. So in this paper, this Wasserstein GAN paper, they show that that you can think of cases where actually the gradient that you would get, the gradient that you would get would be 0 in most places, but then you would actually get a value in one place, which is very difficult to optimize. So the main idea behind this Wasserstein GAN paper was that you can actually define a different metric to optimize, namely this Wasserstein metric, and that will actually allow you to have a continuous metric along which to optimize. So this Wasserstein metric, which is also sometimes called the Earth mover's distance, is just a way of essentially saying how much cost would I incur by moving all of the points on one distribution over to another distribution. So you're kind of moving the Earth, you're moving your entire distribution from one distribution to another, and that's defined in terms of just what's the distance between the samples from your generated distribution and like the closest thing you could get to in your real distribution. And in practice, you actually can't optimize this Wasserstein metric because it's intractable to evaluate, but you can, if you restrict the class of discriminator functions using some tricky techniques, then you get this slightly different way of optimizing a GAN. And you can enforce this through weight clipping or like a gradient penalty. And in practice, these typically work much better than regular GANs. Another cool extension of this is inference. So up until this point, we've talked about how these implicit models will generate samples just fine. But as we talked about previously with latent variable models, we'd like to be able to take a data example and actually generate or infer what is the latent variables that would have given rise to this example. So that's really useful for kind of semi-supervised learning or other latent representation learning. So we want to learn to infer a latent representation. And there's actually 2 papers that came out with methods of doing this. One of them is called adversarially learned inference, or ALI for short. And then the other one's called adversarial feature learning. And the main idea is just that in addition to this regular GAN-style model, where now you take your latent variables, sample from those, generate some observations, you have this kind of symmetric process where you take your true data examples and map those into the latent space, and then you have your discriminator try to discriminate between pairs of observed and latent variables. So now you're learning both generation and inference jointly. And in practice, you can use these to do really, really well on semi-supervised types of learning tasks and other representation learning schemes. So just to cover some applications, the GANs have been used to do this type of image-to-image translation, where if I give you, for instance, a map of all of the objects on a road, then I want you to generate an image that looks like a plausible actual road image. And likewise, you could do the same for like, street view images, of being able to actually generate what is the road map based on some aerial image, or just try to take a sketch and generate what is like this product here. And all of this work was based on having actual correspondence between these types of images. And you can actually extend this to do this case where you don't have the correspondence. And in this case, you can think of like translating a zebra into a horse or a horse into a zebra, where these objects might look similar under certain conditions, but you could transform them into each other. And likewise, you can think of like images taken during the summer versus during the winter. You can do this image-to-image translation, which has been pretty cool to see. Another really kind of crazy one is that people have used GANs and these implicit models to actually do kind of experimental simulations, where instead of actually running your particle collider, you can kind of simulate experimental results from the distribution of results that you might expect to see. And so people have done this for like physics experiments. I think people have done this for also like some biology experiments. And there are cases in which maybe this might help in kind of getting some intuition as to kind of the structure of this physical phenomenon. You can learn these interpretable representations, where here you have a bunch of images of faces under different poses and different lighting conditions. And if you impose certain constraints on the model, then you can actually recover some of these underlying so-called factors of variation. So this is really, again, nice if you want to do kind of some automatic discovery of the latent structure of your space, or if you want to do some type of semi-supervised learning later on. A pretty interesting one, which I had to kind of dig around for, is this MIDI net. So they take, I don't know if you're familiar with like MIDI represented music, but it's just kind of a way of representing music in terms of notes automatically. And they can generate samples of these MIDI renditions. Yeah, so it's not just pretty pictures, there's also music and other components to it too. And then kind of a crazy one was actually taking text and translating that into image. So if I give you a description of a bird here, can you translate that using a generative model into an image of that bird? And so this is this stacked GAN paper where, for instance, here you have this bird is red and brown in color with a stubby beak. So then you generate something that looks plausibly like this. So this is kind of a cool thing if you want to try to like illustrate some set of text. So let's recap implicit models. This is kind of the general setup, at least for GANs, where you're trying to just directly generate this example. So the pros of this method are that you can actually learn these very flexible models without having to define some explicit probability distribution. And you kind of need fewer modeling assumptions because you kind of leave it to the model itself and to the discriminator to figure out what is a good way to define what is a good sample or not. So you're actually learning some components that previously we were just kind of hard coding. And you are able to learn latent representations with these models that you can then use for semi-supervised learning and things later on down the stream. Unlike autoregressive models aren't as good for that, and other latent variable models are typically good at doing this. Some of the cons are that, as we talked about, it's really difficult to evaluate these models. They can be a bit sensitive in terms of their optimization, although there's some work that's been performed in actually improving this. And you can have some difficulty in incorporating model assumptions. So if you want to just generate any kind of data structure, that might not necessarily be as easy. This is something that's maybe shared across more generally all latent variable models. So just to close out the lecture, I wanted to have a brief discussion just to recap what we've seen. So hopefully I've convinced you that generative models are useful, but just to discuss what are they actually good for. And the way I see it, there's really two areas where generative models can be of a lot of help. And one of them is that you can generate and simulate data. So if you had a very limited data distribution and you'd like to be able to kind of interpolate in this space and get a better sense of this data distribution, then it's really nice if you want to generate new images, new experiments, new music, things like that. So if you really care about having these samples, they're useful. And then the other reason is that you can extract structure in this totally automated way. And this is incredibly useful because supervised learning clearly has some limitations that we would like to be able to get over. So what is next for generative models? And this is by no means a comprehensive list, but some things that I think are very interesting and exciting is that you can apply generative models to new forms of data. So far, it's really just been like these simple image data sets and like very simple like speech data sets and things like that, and text. But it really remains to be seen how we scale these models to much larger domains where we have, for instance, like DNA, and we'd like to be able to generate like plausible combinations of DNA, or just like astronomy data and being able to capture some of the complexity that's inherent in that. One thing that I'm particularly excited for is the day when you can just tell your phone or whatever that you want to listen to music of a certain genre and it just writes it all for you in real time. So you can imagine like having this kind of on-demand art, on-demand TV, on-demand everything, where you can kind of say what types of things you prefer and it will give you things within that kind of domain on the fly. And then the other really useful thing about generative models is that they can be incorporated into these other learning systems. So you can incorporate generative models with reinforcement learning, with supervised learning, and actually make the entire system a whole lot stronger. And it seems that, at least for reinforcement learning, generative models really are the key. Like I don't think we're going to be able to learn very complex reinforcement learning algorithms for robotics, for instance, purely through reinforcement learning. And it's already starting to be kind of apparent that you need some of these auxiliary kind of reconstruction or prediction tasks that are, that's the cornerstone of generative models in order to actually learn these reinforcement learning models. So if you have interests in actually building robotics and things like that, then definitely generative models are the way to go. And that's all we have.